Hey guys, welcome to our today's video of the playlist. So today we will be covering the topic queues implementation using linked list. So before hopping into the topic, we need to know first very basic things, which are what is queue and what is linked list. So what is queue? So queue is basically just as simple as stacks. So what happens in stack is that there is one end of the stack is being closed, the other end has been open. So in queue, here you can see that both the ends are open and it follows the rule first in first out. So when you go in the queue, you go from the one end and you go out from the other end. So that's how it works. And what is linked list? So linked list, here we are talking about the singly linked list. So it has nodes, and those nodes consist of two parts. The one is the data and the other is the address of the other node, right? So this is pointing towards the address of the node of the next node. So that's what linked list is. So these are the prerequisites which you guys should know before hopping to queues implementation using linked list. So breaking down the topic, queues implementation using linked list, we first should know what is queue and what is linked list. So we have got a queue here, and what all things we have got here we would see one by one. So we have got a head pointer here which is pointing toward the first node of the queue and which is containing the address of the first node. And here in the queue, each node is containing the address of the next node. So 250, the first node is carrying the address of the second node, and this is 400, so it's carrying the address of the third node, and they are pointing towards each other. So we have got a queue here, and then at the very last, you would see here it is containing a zero, a null value, because it's not pointing towards anything. So it's the last node of the queue. So this queue should follow the basic rules of queues. That is the first in first out rule, right? So there are basic two operations in queue, which is insertion and deletion. So insertion would take place from one side and deletion would take place from the other side. So whenever I want to add a new node, I would add it from one side, and whenever I have to delete a node from the queue, I would delete from the other side. So yeah, and the insertion usually takes place from the rear end, and deletion takes place from the front end. So add from here and delete from here. Now this is the first rule of queues. So the second rule is that the enqueuing and dequeuing process. So what all we are doing here is that we are enqueuing a new node here, right? We are enqueuing a new node and we are dequeuing a node when we are deleting a node. So the process of enqueuing and dequeuing should have the time complexity of order of 1. So we have to make sure we have to maintain the time complexity of order of 1 while enqueuing and while dequeuing, means while inserting a new node and deleting another node. So deletion would take order of 1, so I would show you how. So whenever I want to delete a node, when I want to remove a node from the queue, what I would do is that the pointer let's say I want to delete this node. So I would take this pointer, I would make it point towards the next node, and then it would contain the address of the second node, and then this link would be broken and it would get deleted, right? It's as easy as that. In order to delete or in order to dequeue it, we just have to change the pointer from one side to the other, one node to the other. So it only takes us the time complexity order of 1. So I would just write it here. Yeah. So the process of deletion takes order of 1. But what about insertion? We have to maintain order of 1 while inserting and deleting both. So let's get back from where we started. Okay. Yeah. Now we are back here. So what happened is that while inserting a new node, you have to access this node, right? In order to access this node, you have to iterate through all this queue. So let's say we have a pointer. We need another pointer, right? So let's say we have this pointer variable which is pointing towards the first node, and then it has to iterate through all these nodes in order to reach the last node, because we can add a new node only on the last node, right? So in order to reach this, whenever I would reach the last node, so I have the access of this last node, and I would be having a value, its value, let's say 400. Now I could add a new node to it, but in order to reach this, in order to reach the last node, I have to travel through all this queue. So the time complexity here would be order of n, right? Because it has to iterate n times. The n is the value of the number of nodes in the queue. So it has the time complexity of order of n. So that's not what we want. We want order of 1. So what is the solution to this? What would be the solution to this? So the solution of this would be very easy. So what we can do is we could have a tail pointer. As we have head pointer, we could also have a tail pointer, right? So let's say this is a pointer, this is a tail pointer, which is having the value 400, right? So now we have a head pointer and we have a tail pointer. So tail pointer is having the address of the last node. Now in order to access the last node, we have the tail pointer, and if we have to add a new node, let's say we have this new node. So in order to add this new node, what we have to do is, all we have to do is that we need to have the tail pointer pointing towards the new node, and then we could have the link between this nodes, and it would contain the value of this node, which is, let's say, 500. So it would contain the value of 500, and it will also contain the value of 500. It's as easy as that. So the time complexity here was order of 1, right? Only what we have to do was that we have a tail pointer which is pointing to the last node, and we just have to point the tail pointer to the new node. So it takes the order of 1. So now that we have following all the rules. So while enqueuing and while dequeuing, we are getting order of 1, and insertion and deletion would take place from the rear end, and deletion would take place from the front end. So now we are following all the rules of the queues, so we are good to go, and this is how queues are implemented using linked list. And now we would see the algorithm. So before going to the code, we need to understand what all we are going to fold, right? So first, in order to have a queue and a linked list, we need to have a node. So we would create a node using struct node. That is the first step, and the second, we would initialize 2 pointers, which is the front and the rear, which are the head and tails of the queue. And then third, we would be defining few functions, which is, you define the enqueue function, then you define the display function, then the dequeue function, and then the peek function. These are the functions which would be covering, and at the very end we would be calling this function in the end main. So that all things which we are going to do in the program. So let's get back to the code. Yeah, so first of all, we have got all the necessary libraries which is required, and we have include bit/std++.h, and then we have used using namespace std, which is pretty common. And then what all operations we are going to do is that we would first enqueue 5 in the queue, we would then add 0, then -3, and then we would display it, and then we would dequeue it, and then peek into the queue. So these are other functions which we are going to use in our program, and we would see, and we would define each of this function. So before going into every aspect of it, first of all, we need what do we need. So the first thing which we need is the node. So in order to construct this node, we would use struct node. We would define the data type node, and then in that we would have a node consisted of 2 things. The first part is the data, and the other part is the address of the next node, right? So node asterisk s node asterisk next, and yeah. So now that we have constructed a node, now how many total how many pointers do we require? So we require two pointers. One is the head and the other is the tail. So we would have a struct node front. We would call it the front pointer and the rear pointer. And it would be initialized as 0 because it's not pointing towards anything. So the queue is so there are no nodes in the queue. So it's not pointing towards anything. So initially it would be initialized as 0. So node rear also would be equal to 0. Now that we have created a node and we have two pointers with us, now we would write the enqueue function. So we would call it enqueue, and then we would have an integer called x. So x is so 5 is the value of x here, exactly what we are trying to do. So it would have the value x, and then we would create a node using malloc allocation. So how would we do that? Is that we would be doing struct node as new node. So we are having a new pointer here. So we need a new node in order to point towards in order to add the new node to the queue. So yeah, so we have that new node, and now let's define it. New node is equal to struct node abstract. So we are typecasting this, so that's why we are writing it. We have typecasted, and then we would use the malloc function. So what is malloc function? So it locates to the memory dynamically. So we are using malloc function here, and we would have the size of the struct node. So the size can be anything. It could be 8 bytes or 4 bytes. It totally depends on your compiler. So now that we have our void, we have our void queue. Actually, it's not completed yet. So um, we would have the new node. The date it has the data pointing towards x. Data is the x and new node, and as it's a new node, so it has it contains the address 0 because it's not pointing towards anything because it's a new node. So it's not pointing toward any other node. So here the next value would be 0. And now we would check if the queue is empty. So how would we do that? Is that we would add a if condition to it. So if front is equal to 0 and rear part also is equal to 0, rear pointer also is equal to 0, then front equal to rear equal to new node. Then if the queue is if there is nothing in the queue, then the new node would then the front and the rear both would be point towards the new node, right? So yeah, and else if there is nothing, then if there is something already, then rear would point and next would be equal to new node, and rear equal to new node. Now we have the enqueue function totally ready with us. Now what next we would do is that we would display it. We would define the display function. So display function would be here it goes like this. We would have a temporary pointer. We got struct node temp, and then we check again and we would check this condition again. So I would just copy paste it. But then we would have if the queue is null, then we would print like this, right? Queue is empty. Else temp is equal to front, temporary will be initialized to front, and then while temp is not equal to 0, so it would iterate in the queue, and it would do so till it's 0. So that's why we have a while condition, and then printf percentage %d temp data. It would show the data, and then temp would be equal to temp the next one. So it would go to the next node of the queue. So yeah, we have got now we have an extra bracket here, I guess. Okay, we have to end this also. I'm just checking the brackets, okay? So it's all good. If, else, while, perfect. Now we have done the void display function. Now we would have the void dequeue function. So what void dequeue function does is that it dequeues from the queue. So we would have another pointer which would be our temporary pointer. So just the same as before which we used. Now temp is now we would write temp in the front, right? Now we would have the same check if the queue is empty or not condition. So printf the queue is empty, and yeah. So else printf percentage %d front data. Front would consist front data, and then front equal to front next. It would go to the next node, and we would free the temporary pointer. So now we would just free it. So free function just removes it completely, and yeah, we have the else condition here. Yep, I'll just check the brackets. Perfect. Now we have got the enqueue function, we have got the display function, we have got the dequeue function. Now we just need a simple function which is the void peak function. So void peak. So we are just peeking into the queue. So peeking means having a glance. So we would check the same condition if the queue is empty or not. So if I will just copy paste here, if the queue is empty, then print that the queue is empty. But if the queue is not empty, then print percentage %d the front data. Just end the statement here, and the statement here, and the statement here. Yeah. Now we have got the peak function also ready. Now I would just run and see it. Okay, we have got minute errors. So it's on line number 20 and 24. Yeah. So print and also printf. Okay, on the line 66 we need to write printf and the else condition expected unqualified entity. So wait a minute, I'll just check if else rear is equal to pointing towards the next, which is the new node, and then rear is equal to new node. There is some mistakes in the brackets. I have had an extra bracket here. Yeah, now I guess it would work perfectly. Yeah, exactly. Now we have what we have in the queue is that 5, 0, minus 3, and then we displayed it, and then we dequeued it, and then we peek into it. So this is the code of how queues are implemented using linked list. Thanks for watching.